nervous systems are much more interested in edges than in absolute quantities. Let's have a look at that a bit more closely. So the two questions I want to ask ourselves. One is, why? Why are they interested only in edges, or mainly in edges? And two, how? So let's start with why, first of all. Let me show you an image. Very simple. Imagine that this whole rectangle was an image that I want to send to your computer, which is exactly what is happening at the moment. My computer screen, or I don't know whether mine is, but many computer screens have something like 1366 by 678 pixels. So if I want to send this image to fill your screen, I would have to send you 1366 times 768, which comes to just over 1 million numbers. They're all ones or zeros. So I got 500,000 zeros and 500,000 ones. That's what it takes to send this image to your computer. But you would have thought, actually, I'm going to be really smart here. I can make this a lot simpler just by telling it that all the ones on the left are ones and all the ones on the right are zeros. It's probably the other way around, actually, depending on how you code it. But you get the idea. And that's kind of what the nervous system does. It just says, well, all I need to know, all that's really important here is I'm not interested that it's absolutely black or even that it's absolutely white. This tells me something that what's important here is that there's this edge here which could be useful for figuring out what's there. So all I need to do is to encode this edge, and then I can discard all that, I can discard all this, and then really then all I need now is 768 numbers, and to tell you, actually I need 769 because I need one number to tell you that which direction the gradient is here, whether it's black to white or white to black. So I've now saved an awful lot of your bandwidth. Right, so that's the reason then why is because of bandwidth or coding efficiency. Now remember, the eye, for example, just wants to know what's out there. It's not too interested in the absolute level of light. If it kept that sort of information, we wouldn't need photometers and things like that. So that's what. Now the question is how. Let me show you how it can be done very simply. So imagine that I've got my light stimulus again here, and what I'm going to do now is to make it a bit simpler, I'm just going to cut a line right through the middle here. So now, instead of a 2D image, I've simply got my light level, which is kind of like doing that. Right, so that's light and that's dark. Now what I'm going to do is I'm going to arrange my photoreceptors underneath here in a neat row. Let's label them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, just for completeness sake. Now what I'm going to do is I'm going to have a really simple rule, and that is inhibit your neighbours. On both sides. Right, so 1 inhibits 2, 2 inhibits 1, and 3. 3 inhibits 2 and inhibits 4. Let's see what happens. Right? So let's start on the right-hand side, where we've got I'm ignoring the fact that actually photoreceptors respond to dark and not to light. But let's just try and keep things simple, shall we? So let's start with number 7. Right? So number 7, what's happening with number 7? Well, it's getting stimulation from the light. So that's what colour should we have for that? We should have yellow. So 7's being stimulated by the light, so we've got a plus, but so is 8 and 6. So that means they've got 1 plus. So let's do plus, plus, plus. But I'm also being inhibited by 6, so that's a minus, and I'm being inhibited by 8. So that's a minus. That gives you now minus 1. And the same, I think you can see the same argument will apply to 8, 9, and 10. Right. Now let's have a look at number 6. Number 6, we said, is being excited by the light. It's going to be inhibited by 7, which is a minus, but it's not being inhibited by 5. So we've now got 0. 5 is not being inhibited, it's not being excited by the light. It's being inhibited by 6. So that means we've got 2 minuses, which is a minus 2. 4 is not being excited by the light. It's not being inhibited by 5, and it is not being inhibited by 3 because there's no signal there. So that means we now have 0, and so on along here. So now if we plot those up, what we've got is 0, 0, 0, minus 2, sorry, and let's also say that it's worth minus 0.5. Now, you'll see what I mean in just a minute. So let's just go starting from the right. Now I know that light usually inhibits photoreceptors, but let's just ignore that for a minute. Let's start with number 8. Okay, so what has 8 got? Well, first of all, we've got light coming in. So light is stimulating it. So we've got plus 1, if you like. But it's also getting inhibition from 7. So it's minus 0.5. And from 9, which is minus 0.5. So the sum here comes to 0. The same will apply to 9 and to 10. So in other words, the excitation from the light is being counterbalanced by the inhibition from the neighbours. The same will happen with number 7. But what about number 6? Let's work it out. Number 6 gets input from the light, which is plus 1. It gets inhibition from 7, which is minus 0.5. But 5 isn't being excited by the light, so we don't get any inhibition from 5. So the sum here is 0.5. 5 is not getting inhibition from the light. Sorry, not getting excitation from the light. It is being inhibited by 6. So we've got minus 0.5. So that gives us to minus 0.5. 4 has no light, no inhibition from 5, and no inhibition from 3, so that comes out to 0. So 4, 5, 6, 7, 8, 9, and so on for 3. So now if we plot these, what we got is so 0, it's got 0, 0, minus 0.5, plus 0.5, 0, 0, 0, 0. We have got an automatic edge detection. So it's detecting the edge, and it's also actually increasing the contrast. So just from having a simple rule, we end up with edge detection. And that's a much more efficient way of sending information up to the central nervous system.